Perfect. All right. Good afternoon, everybody. It's good morning for me, but thank you very much for inviting me to speak today. And I'm going to talk about prevention as it relates to cleaning and maintaining your stainless steel equipment. So not necessarily a process system, but your heart of your process, your vessels, your stainless steel, how to make sure that they are maintained, that the surface is passive, that you can maintain that nice, clean, passive surface. So we're going to talk about a preventative approach, or looking at how to treat them using your lean tools that you already should be practicing. So with that, we're going to move into the agenda and hopefully get that off of here. So we're going to talk about the applications for acids in biopharmaceutical sites. So where are acids being used right now, and how are they being used, and are they being used correctly? We're going to introduce the total predictive maintenance concept as it relates to stainless steel maintenance and passivation and derouging. I'll have an example of a risk ranking or a risk ranking or a risk assessment of stainless steel, of recommending a frequency and how to come up with that frequency for your equipment for derouging and passivation, and then some science-based tools to help you develop the predictive and preventative maintenance approaches with some case studies. And then we'll just talk about wrap it all up with some added benefits for acid. So as far as where they're used right now in biopharma, they're used to clean inorganic residues. So any kind of metal oxides, any type of, derouging applications, glassware, things like that. They're used for pH adjustments, viral inactivation. So acids are already being used in the facility. Corrective maintenance of stainless steel. So that would be, when you come into your tank and you look at your tank and you see visible rouging. So you may have to take that tank out of service and then implement a corrective action, whether that's passivation, derouging, electropolishing. There's a number of things that you can do once you get into that corrective maintenance, but you don't want to live in that space. You want to be preventive, but you want to have some sort of thought process to your prevention. Most people right now, what they do is they just assign a PM based on a time-based prevention model rather than a data-driven reaction, or I guess we're not reacting if it's data-driven, but more of a data-driven model. Acids can also be used as buffers, process solutions, and your preventive maintenance. So as far as reduction of acid, so what you want to do, the goal is to be in front of your system, in front of the rouge. You don't want to let your tank look like the image of the tank on the right. You want to be preventative, but you also want to have that knowledge and that data set to be predictive. So you have the three models here. You have your routine maintenance that you're doing. It's that routine maintenance when somebody opens up the tank and they see an issue like this and they say, okay, we need to do some sort of maintenance. Preventive maintenance is doing it on some sort of a frequency. So that would be, okay, every 6 months, we are going to do a derouging and passivation. And a predictive model would be building that data set to extend the time between. So your preventative maintenance may have been once a month or every quarter, but maybe that predictive model, you can stretch that out and do your passivation, and if you need derouging, and do that once per year, or whatever that data indicates that you should be doing it. You can set markers to trigger that maintenance event using the tools that I have in the lower left or lower right hand corner. So the tools are, you have an EC pin or electrochemical pin that you can detect the passive surface. There's salt spray cabinets, there's copper sulfate tests. So there's a lot of different methodologies out there, but predictive modeling really leverages those statistics to predict the outcomes. Most often your event that you want to predict is in the future. So predictive modeling can be applied to any type of unknown event. And this would be, the opposite of that, or not really the opposite, but preventative maintenance is really those daily maintenance to prevent deterioration. inspections to measure deterioration, regular operating checkups, and early treatment. So that, you know, you're doing that on some sort of frequency, but you really want to build that risk in there. So, you know, Industry 4.0, we hear that a lot. It's squarely in the area of condition monitoring and predictive maintenance. So, you know, they're not new concepts. They've been a reality for a few, but it's really what we should aspire to. So looking at passivation, I hope you can see the top of my screen, but the passivation process comparison. So I have some typical acids that are used in industry right now. All of these are referenced in either the ASME BPE or the ASTM 967 guide or documents out there. So, you know, the image here on the right is an SEM image of stainless steel. So it's scanning electron microscopy image of a 1200 X with a 6 millimeter distance and a 40 micron area of a stainless steel, of 316 stainless steel with an RA of 20. And what I have, why I have this image here is that when you think of stainless steel, it looks smooth to the unaided eye. But you all know that there is a roughness average to stainless steel. So your roughness average measures your peaks to your valley, your distance, and it averages them. So there's some amount of grit to every stainless steel surface. And why you want to prevent rouge from happening is you start getting the rouge and into these granulars of your stainless steel so that you can build up in those. And the idea is you want to be able to lift all of that out of the crevices, not only from the surface of the stainless steel, but include those crevices. So there's nitric acid, citric acid, phosphoric acid, chelant systems, and formulated acid blends. So, you know, there are advantages for using, you know, citric. It is generally recognized as safe, or it's GRAS, it's food safe. But there are safety advantages rather than using nitric acid. So nitric acid, it attacks the iron first, but it also diminishes all the other elements in that alloy. So they're removed as well. So what it does is effectively takes off your first layer of your stainless steel, and it takes off your chromium level as well, your chromium oxide. So it'll take it down to a certain depth, but then it has all of those heavy metals will be in your waste at that point. So, you know, you may have an added expense there if you're going to use nitric acid, which by the way is the gold standard, but there are certain safety issues that are inherent with using nitric acid. So you may have expensive transportation costs, hazardous waste disposal. It's an oxidizer, so it'll definitely increase your risk and your expense to disposal. You know, citric acids and phosphorics are referenced in the ASTM 967 and the BPE, so they are safe. You can use less concentrations when you look at your concentrations of your citric acids compared to, you know, compared to your nitric acid at 10 to 40%, with your citric acid running around 10 to 15% recommendation or recommended concentrations, your phosphoric acid at 5 to 25%. So, you know, a little bit higher, but you can go a little lower depending on your level and what type of rouge. You know, whether it's level, if it's a type 1 or type 2, and the amount. You can add chelant systems in there, but they don't really work well without being added to an acid. So you really want to, if you're going to add a chelant system, you want to add that to an acid. The formulated acid blends, they can be used at less concentrations, so between 1 and 15%, depending on your level and type of rouge. Again, 15 minutes to 4 hours. So they are definitely more efficient when it comes to timing, because the upper end, you know, is in alignment with the others, but it may not necessarily take 4 hours. They're a broad spectrum as far as the temperature range that you can use the formulated alkaline acid blends, and they will passivate and they will derouge. So this is the one thing. you get that I want you to take home from this slide. If you get anything else out of this slide, there's actually two things. One, nitric acid will passivate and derouge. So it will do that, but you want to add a passivation treatment after that, so you enhance that passive layer. Now, the problem with citric acid, it's great for passivation, but it will not derouge. So it is specific for free iron. And what that means, it will not remove the iron oxides. So that is really one of the most important things, because a lot of times I see people will try to use just citric acid alone. And citric acid is a great passivation chemical, but it is not a great derouging chemical. And you would want to use it in conjunction with your nitric acid that will passivate and will derouge, but it'll take some amount of time to reform that layer because you've stripped everything. So you would want to add a passivation treatment on top of that. Formulated acid blends are blended with both. The majority of the times, or generally, they're blended with both a derouger and a passivation agent, and with chelants and surfactants and everything else that you're going to need to maintain that stainless steel. So that it will get into these crevices and lift. It affects the surface tension of that chemical, and it will get down into those crevices and lift the rouge up. Now moving into different times and concentrations so you can see the differences. When you're looking at passivation testing, so just to show you the difference between a citric acid formulated detergent and a citric acid, we did a treatment where, under the conditions of the study, the images from left to right are a handheld device. So this is your electrochemical pen. This is a copper sulfate test, and this is a salt spray cabinet, which is essentially spraying your stainless steel with the salt and waiting for it to form rouge. But that's, it's effective, but it takes a long time. So a lot of times we didn't implement this if we didn't have the right conditions in the first two studies. So we exposed the coupons to various times and concentration, and these two concentrations here, the 10% formulated detergent and the 3.7 are meant to equilibrate, I guess you would say, or correlate the citric acid concentration to the citric acid concentration in formulated detergent. And you can see here that at 45 degrees C, no passivation occurred under our conditions for the study. And at 60 minutes, no passivation occurred. But at 60 degrees C at 10 minutes, no passivation occurred. And then at 10 minutes, at 70 degrees, that's where we start moving into the conditions and the time it took to provide a passive surface. So you can see here how it is time dependent. We didn't test concentration, but it is concentration dependent, and it is temperature dependent. So those are your critical parameters. And citric acid for 120 minutes at 3.7% volume per volume at 80 degrees C was not able to provide a passive surface. So as far as derouging results, again, this is just a visual interpretation of what we saw. So this is using the 3.7% citric acid, so not 37, formulated citric acid detergent and a formulated phosphoric citric acid detergent. So you can see that the differences even between the two formulated detergents, that there are differences based on the blend. So this is a phosphoric citric and this one is a citric oxalic blend. So you get a little bit better derouging. And this is using a 2% volume for volume, 60 degrees C, 30 minutes with the amount of weight of rouge removal, looking at comparison of deionized water, 3.7% citric acid to two formulated detergents. So another advantage of using formulated detergents would be your rinsing. So as far as looking at a rinse profile, your conductivity rinse, so this would be your citric acid and your orange, and then your blue would be a formulated detergent. So you have less conductivity, less TOC, so you're rinsing in less rinses. So 2 rinses on average for the TOC and 2 rinses for conductivity, but about 3 rinses for your citric acid. So you do see, and again, your TOC is going to come down because of the citric acid being less. But what this does is it'll provide freer rinsing, and you can correlate all of these to your different methods available as far as, for analytical methods, toxicity, stability, preservative effectiveness. So there's other things to consider, but as far as your rinse profile, you are rinsing quicker with a formulated detergent. So what is the regulatory stance on this? Let me see what my timing is. Okay. So as far as the regulatory stance, we are seeing some, these are just some letters that were pulled before. So in 2009, visible rouging was observed on exterior of a chrome skid. GMP trends from 2014, for example, production equipment was observed rusty and showing evidence of corrosion. So, I mean, these are a little older, but it just shows that it's been a focus for a while. As far as, our inspectors looking at this, yes. If they're seeing visible rouge, they know your equipment is not in a good state. So moving into predictive maintenance and lean TPMs, because I really want to make sure I have enough time to get into the case studies. So as far as lean manufacturing, it's really that waste minimization without sacrificing productivity. So what I have here is an image of an 18-wheeler, so a truck or a lorry or whatever you call them in your country. And this is right here is a depiction of a wheel check loose lug nut indicator. So in industry, total productive maintenance is a system of maintaining and improving integrity of production and quality systems through machines, equipment, processes, and employees that add that business value to an organization. So it keeps all equipment in top working condition to avoid breakdowns and delays in manufacturing. So why am I showing this? Well, prior to this, you would have to walk around your truck and take the torque wrench and check each lug nut to make sure that they are all tight. But with this lean tool, with this wheel check lug, loose lug nut indicator, you can see immediately, it's a visual cue, I'm unsafe. So you're not having to go around and test all of them or go to the point of failure to where a lug nut comes loose and your wheel falls off. So they're really, it's a tool. So the total predictive maintenance is a tool to help you gather that data, and it's a quick check to see what your equipment looks like. So it really, by doing the predictive maintenance with your stainless steel, it keeps your stainless steel in that validated state. It keeps it in that visibly clean state. So this is just an example of what I would look at when I was assessing, or if I was assessing stainless steel maintenance based, risk-based versus predictive or process analytical. For that, you want that OEE, or overall equipment effectiveness. So you want to look at your performance, your availability, and your quality. So your performance would be, do you have reduced speed or changeover from batch to batch? Your minor steps and idle time would be your routine maintenance. So are you having to stop to do routine maintenance with your equipment, taking them out of service? Is your equipment available? Is it broken down? Are you having frequent setups and adjustments due to routine stainless steel maintenance? And the quality of your equipment. So are there defects from rouge? This could impact your yield. So all of these apply to stainless steel maintenance, just like they would any system. So looking at your risk analysis, so from ICH Q9, your quality risk management, you want to look at two primary principles, right? So you want to look at the knowledge. So, the evaluation of risk should be based on your scientific knowledge, and it should be commensurate with your level of risk. So as far as, your risk-based, I will show you in the interest of time. So this is just an overview of a typical manufacturing process. And what you could do with this is look at your probability. So these are some things that I would consider if I was doing a risk assessment. So, look at your stainless steel, the type of stainless steel. Do you have high shear forces, the history of the vessel, your surface finish, your water hardness, pH, temperature? All of these things can be considered when you're doing a risk assessment on your stainless steel for implementing a frequency. So looking at severity, these are some things I would look at. So in appearance, obviously, product impact. So is it downstream, upstream, indirect product impact? So all of these could be used to assess severity. So presence of roots, presence of corrosion, microbial excursions, visual inspections. As far as detection, how are you going to detect? So this is where I want to get into, is the detection. So there's visual inspection, surface sampling, particulate testing, TOC, micro testing, endotoxin, iron monitoring, and conductivity testing. So you can use all of these tools, and how are you detecting is going to be able to determine your risk. So if you have data, you know, like the loose lug nut indicator, you have data versus just a visual inspection on some type of frequency, obviously that's going to throw it into a lower risk. So looking at your products, what I did is divided them up into no product contact, your utility systems, indirect product contact, and direct product contact, with your level of risk going up, where you want to have a preventative approach, a predictive approach, and then a corrective approach would obviously be, you know, more risky and more risk as you move closer and closer to your product. So looking at utility systems, you have your water for injection systems, your clean steam, your process water, your gases, and your cooling system. So talking about a utility system, a preventative approach, here's an example of a vessel that had a scheduled preventative maintenance, pre-cleaned with formulated alkaline detergent at 1 to 5% at 60 to 80 degrees, and then derouged at 10 to 30% for several hours. So it took quite a long time for that. And, you know, it did work. The bottom is an image of an autoclave. So you had the what it looked like as found and then after treatment. But what you really want to do is avoid this. This ended up being like a 9-hour derouging. So you don't want to have this. You don't want to let your tanks get to this level. You don't want to let your autoclaves look like this. So you want to get in front of it. You want to build that data set. So how you can do that, there's several predictive tools you can use. There's iron monitoring, non-viable particulate monitoring, viable particulate monitoring, looking at my time here, making sure I'm good, and conductivity monitoring. So there are several tools that you can use, and in the interest of time, because it does go quick and you will have my slides, I just want to go over one case study. So this shows a predictive approach using a case study about buffers. So this is a buffer preparation tank, cleaning and passivation. We wanted to confirm the parameters for cleaning with a detergent cleaning step and evaluate the use of an acid for cleaning and passivation, which was the primary concern at this facility. So the current state of these tanks, there were 200-liter tanks, 1,000-liter tanks, 3,000-liter tanks, and various transfer lines, and they showed no visible signs of rouging. But what they wanted to do was get away from what their current state was. So their current state was to use a 2% alkaline detergent, 80 degrees C for 30 minutes, and then passivate using a 10% acid, 70 degrees C, 60 minutes once per week. What we did is we set up a study to evaluate the passive layer during wet storage of the buffer to reduce the cleaning frequency or the concentration, so both. And as a we actually prepared negative controls where we took a stainless steel coupon, exposed it to the 10% formulated citric acid detergent for 70 degrees, 60 minutes. So we knew it was passive when we started, and then we stored in the buffer at ambient temperature, and it failed at 14 days. So that was our negative control. Or actually, that should be a positive control because we showed, you know, that it failed. But then moving into what we did in the study. So we did a cleaning study. We started off looking at what is the state. So their current state was using that 2%, 80 degrees C for 30 minutes. So we found that we were able to clean it using a 1% alkaline detergent, 5 minutes, ambient conditions. So again, when you're using that 80-degree water, you're having to heat that water up or use a utility where you're providing hot water at the drop. But more than likely, you're having to heat this up in your system, which takes a certain amount of time. So by doing that, you are saving time for the utility heat up. You're saving, you know, the hot water, which is also a safety concern. and less alkalinity. So already the process has been optimized by 25 minutes and then another 20 minutes for not having to heat the water up. Then what we did is we moved into the acid treatment. So we looked at stainless steel coupons exposed to the buffer, and we did a treatment every 7 days and passivated using lower concentrations and lower times and lower contact time. And we looked at a 0.5% acid detergent and a 2% acid detergent. So keep in mind they were using a 10%, and then looked at 10 minutes at the various degrees. So what we found is that looking at an acid detergent at a concentration of 0.5% at 60 degrees for 10 minutes, at 7 days, so doing this once per week, we were still able to maintain the passive surface. At 2 weeks, we were still able to maintain, but at 21 days or 3 weeks, it failed. So it was not able to maintain that passive surface for a long duration. So we couldn't stretch it out to the 21 days. So when we moved into looking at a 2% solution at 60 degrees for 10 minutes, we found that all the way through 35 days, we were able to maintain that surface. So, doing that every 7 days showed that this condition was able to maintain that passive surface, where eventually this one failed. So as the predictive approach, also we looked at the 45 degrees, and that was not able to maintain. It failed after 7 days. So what their new process looks like, to sum up, on day 7, so what they're doing is every 7 days they do an ambient rinse every 7 days, and they passivate using the 2%, 60 degrees C for 10 minutes, and then on day 28 they clean using the alkaline detergent at 1% for 5 minutes room temperature and passivate. So what they're doing is they're saving an overall time savings for the cleaning of this one tank. Just one tank is huge. So they were able to build that data set and predict their point at which they would fail and build the timing in, or the frequency in, to prevent that, so that they didn't have to be reactive to their process. So I believe that is all the time that I have. I can check my phone over here. So again, I apologize. I had a lot to talk about, but it is definitely a lot to talk about in just 25 minutes. So I did want to give you a taste of what predictive maintenance is using the buffer example. So what you want to do is you want to investigate and mitigate your risk on a daily base. You want to understand the data, and then, reduce that equipment out of service, reduce schedule delays, reduce your scrap, and then, call on your suppliers out there as a technical resource and partner, because chances are we can help you with all of this, and as well your other suppliers can help you with that as well. So I guess I can take any questions now.